We're going to continue our chapter on capacitance, covering an example problem from section 3 and then going on to section 4. Okay, let's do an example first. In the figure below, switch S is closed to connect the uncharged capacitor of capacitance C is equal to 0.25 microfarads to the battery of potential difference V is equal to 12 volts. All right, so you have the switch here. You have a capacitor that has some capacitance of 0.25 microfarads. You have the battery that's supplying a voltage of 12 volts. Now, the lower capacitor plate has a thickness of L is equal to 0.5 centimeters and a face area of 2 times 10 to the negative 4 meters squared. And it consists of copper, in which the density of conduction electrons is N is equal to 8.49 times 10 to the 28th electrons per meter cubed. All right, so this is a new variable we probably haven't seen before. It's a charge density in a sense, but it's actually the density of electrons in per cubic meter. So it's not actually a charge; it's just the density of the actual electrons. Okay, so from the depth d within the plate from what depth d within the plate must electrons move to the plate face as the capacitor becomes charged? Okay, so the charge collected on the plate is related to the capacitance and the potential difference across that capacitor by the equation Q is equal to CV. All right, so because the lower plate is connected to the negative terminal of the battery, conduction electrons are going to move up to the face of the plate. So from the equation, the total charge magnitude collected there is just going to be, right, so our total charge is just going to be the capacitance times the potential. So we're given our capacitance, which is 0.25 times 10 to the negative 6 farads multiplied by 12 volts. So we see that our charge is going to be 3.0 times 10 to the negative 6 coulombs. Now, dividing this result by E gives us the total number of conduction electrons that come up to the face. Right? So this is our total charge. If we divide it by E, that's the charge of an electron. That's going to give us how many electrons are actually in this amount of charge. All right, so N, this is now capital N, which is different from little n. Little n was going to be our density of conduction electrons. N is just what we're going to use for the number of conduction electrons. And in physics, we usually use capital N to dictate or to denote the total number of something physical. Okay, so this is just going to be the charge divided by E. So we have 3.0 times 10 to the negative 6 coulombs divided by E, which is 1.602 times 10 to the negative 19 coulombs. So this gives us a value of N that is 1.873 times 10 to the 13, and again, this is the number of electrons. So these electrons come from a volume that is the product of the face area and the depth d that we're trying to seek. So the density of conduction electrons per unit volume can be written as such. So the density of electrons is just going to be the number of electrons over some volume. And in our case, the volume is just going to be A times D. Now what we're trying to find is our D. So really we want D is equal to the number of electrons divided by A times the density of electrons. All right, so then we just solve for D. It's the number, it is going to be the number we just found, which is 1.873 times 10 to the 13 electrons divided by our area, which is 2.0 times 10 to the negative 4 meters squared, which is given up here in the problem, multiplied by our charge density, which is also given up here in the problem, or the electron density, I should say. So that is 8.49 times 10 to the 28. And the unit for that is electrons per meter cubed. So then solve this out. We find that our distance is going to be 1.1 times 10 to the negative 12 meters, or 1.1 picometers. So again, this was going to be the depth within the plate that electrons must move to the plate face as the capacitor becomes charged. All right, so the electrons from that region get pushed onto the plate of the capacitor. Okay, let's go ahead and move on to the next section. So now we're going to talk about some parallel and series circuits, and how we can calculate capacitance and voltage and charge when we're dealing with these circuits. So when a potential difference V is applied across several capacitors that are connected in parallel, that potential difference V is applied across each capacitor, and the total charge Q stored on the capacitors is just going to be the sum of the charges stored on all the capacitors. Okay, so what does that mean? Well, something in parallel is going to look like this. You have a lead coming from one end of the battery that goes into one end, and then another end of the battery into the other end. And then same for all of these, right? So these are all going to be in parallel. And in a second, we'll see what a series circuit would look like and how that's different. All right, let me just go erase that. So what we're saying is when you have this potential across the capacitor, which is the same as across the battery, is going to stay the same for each capacitor. All right, so when something is when the capacitors are in parallel like this, the voltage across each capacitor is the same. And the total charge stored on the capacitors is just the sum of all the charges stored on each individual capacitor. Right, so the total charge of the circuit is just going to be Q1 plus Q2 plus Q3. Oops. Okay. The capacitors connected in parallel can be replaced with an equivalent capacitor, and it's going to have the same total charge of each of them added together, and then the same potential difference, V, as the actual capacitors. So the potential difference is just going to be the same over it. So you can take this circuit and just simplify it to one circuit that has some equivalent capacitance. So we need to figure out what that equivalent capacitance is. The capacitance is going to be over the same voltage, V, and over all of the charge of each of the capacitors added together. So what does that look like? Well, if you have the charge for each of these capacitors, and you just say, well, the total charge is going to be all the charges added together. So you're taking these equations and you're simplifying it to this. So you're saying that all the charges added together, 1, 2, and 3, is just going to be equal to all the right side of the equations added together. And since V doesn't change for each of these, you can multiply each of the capacitance by V. Now we want to find what the equivalent capacitance is, so we just divide this total charge that we found up here by our voltage. And that's just equal to all the capacitors added together. All right. So really, if you want to know what the total capacitance of a circuit is that has all of the capacitors in parallel, you just add all the capacitance together. All right, so the equivalent capacitance is just going to be the summation of 1 to however many capacitors that you have of the capacitance. You just add them all together. Okay. Now, capacitors in series are going to work a little bit differently. So again, something in series is going to be ones that it basically goes from end to end. So you have a terminal that comes in from one end, and then the other terminal goes into the next one, and the other terminal goes into the next one, and the other terminal goes all the way back into the battery. So when a potential difference, V, is applied across several capacitors connected in series, the capacitors have identical charge Q. So now each capacitor is going to have the same charge, and the sum of the potential differences across all the capacitors is equal to the applied potential difference V. So you're going to have a V1, a V2, and a V3 across each of these capacitors. And it's going to depend on what the capacitance is and also the charge, which is going to be the same across all of them. All right, so this Q is the same as this Q is the same as this Q. All right, so our voltages could be different depending on, again, what the capacitance is. Okay. So the capacitors that are connected in series can be replaced with an equivalent capacitor like we did before. So we can take this circuit and simplify it to this circuit. And it's going to have the same charge Q as each of the individual capacitors, right? Because they all have the same charge. And the same total potential difference. So when you add V1, V2, and V3 together, you should get this V here, right? The total potential difference, or the voltage drop across the capacitor, or across the circuit. Okay, so what does this look like? Well, we know that you're going to have different voltages for each, and you have different capacitance for each capacitor. But Q stays the same. All right, so we're going to keep that as just Q. So if I wanted to find what the total voltage is, you're going to add all the voltages together, which is just going to be equal to V, like we said, is just going to be the voltage of the battery. And the right side of the equation is just going to be the charge, which does not change, times 1 over each of the capacitance. All right, so the equivalent capacitance is then going to be 1 over each of these, 1 over all of these. All right, so to simplify that, it's just going to turn into this. So 1 over the equivalent capacitance is equal to the sum of all of the capacitance, 1 over all of the capacitance, right? For however many capacitors you happen to have in series. All right, so let's go ahead and do some examples. So we're looking at capacitors in parallel and in series at the same time for this one. So it's asking us to find the equivalent capacitance for the combination of capacitances shown in the figure across which potential difference V is applied. All right, so assume, and they give us what the capacitance are. So the first thing we want to do is reduce the circuit to a single capacitor, right? So that's going to help us figure out what this equivalent capacitance is. So by doing that, first thing we want to do is take these two in parallel and combine them into one. So these two are going to get combined into that one. All right. Now, since they're in parallel, we know that the capacitance can just add together. So if we take capacitance C12, which is the capacitance of 1 and 2 together, that's just going to equal to, C1 plus C2. Right, so that's just 12.0 microfarads, right, as given here, plus 5.3 microfarads. And that gets us 17.3 microfarads. All right, so now we're down to a circuit that has two capacitors, and they're both in series. So now we want to go from this to just one capacitor. So to do that, we want to use the equation for a capacitance in series. All right, so C123, because now we're adding C12 and C3 together. So now we're at C123. That's just going to be equal to 1 over, this is 1 over C123. 1 over C123 is equal to 1 over C12 plus 1 over C3. That's going to be equal to 1 over 17.3 microfarads plus 1 over 4.50 microfarads. And that's equal to 0.280 microfarads. To the negative 1. So if I want to then find what actual, so this was 1 over C123. I want to find the, what C123 is, right? Just so it's in the numerator. So C123 is just going to be 1 over 0.28 microfarads to the negative 1. So I get 3.57 microfarads. Right, so that is what our equivalent capacitance was going to be. Right, so really, you get whatever this sum is here, and you take the reciprocal of it. So you get, because it's equal to C123, so you want to get the reciprocal, and that'll give you what C123 is. All right. All right. So next we're going to look at figuring out what each of the charges are, specifically what the charge on C1 is. So if the potential difference applied to the input terminals in the figure is 12.5 volts, what is the charge on C1? All right, so the first thing that we want to do, if we want to find the charge on this specific capacitor, we have to first put everything into one capacitor. So simplify the circuit down to one capacitor. And what that'll do is tell us what the equivalent capacitance is. And then we would also know what the voltage is across the entire, this one simplified capacitor. All right, so we did that in the last step. All right, so at this point, we need to work backwards back to the desired capacitor. Okay, applying Q is equal to CV yields the charge. So if we want to know what the charge is of this one capacitor, because again, we're trying to find the charge of C1, so we need to first find a charge of what just this one capacitor is, because we can do that simply since it's a simple circuit like this. We could say that, well, Q of 1, 2, 3, which is all of them added together, is just going to be equal to C of 1, 2, 3 times the voltage. Okay, so that's going to be our result from last time, which is 3.57 microfarads, multiplied by our voltage, which is 12.5 volts. All right, oops. So the Q that we get, Q123, is then equal to 44.6 microcoulombs. Okay? So now that we found the charge, we know that series capacitors and their equivalent have the same Q. So if this is the Q of the combination of them, each of the ones in series are also going to have that same Q. Therefore, Q12 is going to be equal to Q123, where Q12 was that one when we broke it out and then we had this, just this top capacitor here. If you remember, Q12 is again both of these capacitors together. All right, but since they're both in series, we can say that they're the same. All right, so when we say they're the same, Q12 is again just going to be 44.6 microcoulombs. Okay. The next thing we want to do is apply the same equation, but now solve for V because it yields the potential difference. All right, we're going to need to know the potential difference to find what the charge is of these. All right, so if I found the potential difference, V12, and that's just going to be the Q12 divided by C12, I find that the potential difference, so this is just 44.6 divided by 17.3, where this was microcoulombs and this is microfarads. You get 2.58 volts. Okay, so that's going to be our voltage across our capacitor, our top capacitor, which is again 1 and 2. Okay. Now we need to know that, well, since we have now a parallel capacitors, these two parallel capacitors, the voltage across them is going to be the same. We said that previously. All right, so the voltage across parallel capacitors is going to be the same. All right, so because of that, we can say that, well, V1, which is the voltage across the capacitor we're trying to find the charge of, is equal to V12, which is the voltage we just found. So that's 2.58 volts as well. Now, if I wanted to find Q1, well, I just found the voltage for the voltage for this capacitor, and we know what the capacitance is, so I can find the charge. All right, so we're going to use the same equation, but now solved for Q. It's going to be C1V1. So that's just equal to 12 microfarads, which is given to us, times 2.58 volts. And we see that our Q1 is equal to 31.0 microcoulombs. Okay. So the trick here again was to take our complex circuit, combine it into one, and then work our way backwards knowing the rules that we know about circuits. So we know, again, that series capacitors are going to have the same Q. We know the parallel capacitors are going to have the same V. And they have these fun little naming schemes if you want to memorize those. So you have series Q, and you have par V. Series Q and par V. Okay. All right, I know we're going a little long here, but I do want to get through this last example before I finish up this lecture. All right, so we're talking about now one capacitor that's charging up some other capacitor. All right, so capacitor 1, which has a capacitance of 3.55 microfarads, is charged to a potential difference of V0 using a 6.3 volt battery. The charge is then removed, and the capacitor is connected, as shown in the figure, to an uncharged capacitor 2 that has a capacitance given. When the switch S is closed, charge is going to flow between the capacitors. Now find the charge on each capacitor when equilibrium is reached. Alright, so initially the first capacitor is going to be connected to the battery. Excuse me. And the charge it acquires is given from the equation. Right? So the voltage is going to be the voltage across the battery, and the capacitance is given to us. So the charge of this original, the first capacitor when it's connected to the battery will just be given as such, right? You're just going to be multiplying the capacitance times the voltage. Now, when the switch S in figure 2511 is closed, the capacitor 1 begins to charge capacitor 2. So now you have two capacitors in this circuit. They're going to be in series, and there's no battery attached. The electric potential and charge on capacitor 1 is going to decrease, and those on capacitor 2 is going to increase until you reach equilibrium. All right, so when you have two capacitors in a circuit in series, you're going to have equilibrium be reached, which means V1 is going to equal V2. All right. Well, what that means is we can just plug in each equation for V1 and V2. So again, V is just Q over C. So this is going to be Q1 over C1, which is equal to Q2 over C2. All right. Well, we know that the charge in itself cannot be created or destroyed. So the total amount of charge can't change, which means that Q1 plus Q2 is equal to Q0, where Q0 is our original charge. This is the charge on C1 when it was connected to a battery. So when you have, whatever the charges are when they're connected together, when you add them together, it needs to equal this total charge. Alright, so that lets us get rid of one of our variables. So Q0 minus Q1 is going to be what Q2 equals to. So now I take this result and I plug that back into our equation. And you see that Q1 over C1 is now equal to Q0 minus Q1 over C2. Okay. Now, all I really need to do is solve for Q1. Alright, so with a little bit of algebra, we can get there. Alright, so first, let's say, alright, so we're just simplifying this. Let's say Q0 over C2, because what I did was I said that Q0 over C2 minus Q1 over C2. So just kind of break this part away. And then I moved Q0, and since this is negative, or excuse me, I kept the Q0 over C2 there, and I moved Q1 over C2 to the other side. All right, so when I do that, you get Q1 over C2 plus Q1 over C1. And again, I'm going to solve for Q1. So I want to simplify these together. When I do that, I get Q0 over C2 is equal to Q1 times 1 over C2 plus 1 over C1, which means, again, just solving for Q1 by itself, Q1 is Q0 over C2 divided by this big mess, which is C2 C1. Okay. All right. Plugging in, so we know everything in the right side of this equation. We know the capacitance, and we know what our total charge was. We found that earlier up here. We can just now say Q1 is 6.35 microcoulombs. All right, so I found our Q1. Now I want to find what Q2 is. You can just use any of the equations up here that might be helpful, so let's just go ahead and use that one. So Q2 is Q0 minus Q1. So Q2 is 16.0 microcoulombs. Okay, that's it for this lecture. We'll see you next time.